So in the last couple of videos, we've talked through some of the history of quantum physics and how physicists went from looking at the line spectra, the unique patterns of wavelengths that are absorbed and emitted by each element in the periodic table. From those, the empirical fact of those spectra to Niels Bohr's first quantum model of the atom, which consists of electrons in certain special orbits that don't emit any radiation, and explains those spectral lines as light that's absorbed and emitted only when moving between orbits, with the frequency of the light depending on the energy difference. This is a great model, but it doesn't have any particular justification as to why those orbits should be special until Louis de Broglie makes the proposal that maybe electrons should behave like waves, and then we can think about these orbits as orbits where the wave completing one orbit comes exactly back to where it started, and those waves reinforce themselves through constructive interference, making those states standing wave modes that are special, whereas any other orbit, the waves would destructively interfere with themselves in the next lap and wipe themselves out. This gives you a nice justification for the Bohr model with its special orbits, and conceptually it's not too bad. The idea of electrons behaving like waves, though, is really a weird one, but it turns out there's very direct experimental evidence of this, first seen by Clinton Davison and Lester Germer at Bell Labs in the 1920s, completely by accident, as it turns out, which then shows that electrons behave like waves as they bounce off a surface of nickel atoms, and electrons that hit the very front of the crystal versus electrons that are somewhat deeper in the crystal. Those take two different paths. Those different paths interfere with each other, and you have constructive interference at very particular angles that depend on the wavelength of the electrons. So by the late 1920s, people are completely convinced that as weird as the idea of electrons behaving like waves is, this is a real experimental fact about the world. And this is one of the key things that really gets the field of quantum physics going. Now, if we were in ordinary circumstances and could all be together in ISC, we have some apparatus at Union that does the electron diffraction experiment that Davison and Germer did, something very much like it. And we would have you do a lab where you actually see that and verify that, in fact, the electrons behave in a wave-like manner in the way that they're generally supposed to do. Unfortunately, we have this horrible circumstance, so we're not able to do that. So instead, we're going to use video here of really one of the most beautiful realizations of an experiment I've ever seen, which is a team at Hitachi has a setup where they can shoot electrons one at a time at a fluorescent screen. So when the electrons hit the screen, they make a little dot of light. And you can see these in the video over here that you can see these dots appearing at a particular place at a particular instant in time. And that pretty much defines what it is for something to be a particle. So these are electrons acting like particles. But as you can see in the video, if you repeat this experiment many, many times, right, the electrons initially appear to be distributed fairly randomly over the surface. Now, between the electron source and the screen, they've inserted something that splits the electrons into two possible paths. So there's a double slit there that's forcing the electron to take two different paths. But these electrons are behaving like waves. And if you repeat the experiment many, 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 many times and keep track of all of the detections, you can see emerging in the video, you can see a pattern of bright and dark stripes that is exactly like the double slit pattern that you saw in the Young's interference type experiments that we did last week. Right. Those experiments are what convinced physicists that light behaves like a wave. Doing this same experiment with electrons shows very dramatically that electrons, in fact, behave like waves. And this is a beautiful realization of the experiment that lets you see what's really going on here. The electron is both a particle and a wave at the same time. Each individual electron is detected at a particular place at a particular instant, while collectively, all of them together trace out this pattern if you repeat the experiment many times. Now you might say, well, maybe this is something really special about electrons, but in fact, as quantum physics developed, we realized this applies to all particles, no matter what their mass. Electrons are particularly easy to see this with because they happen to be very small and very light and easily moved around. But you can do this with all sorts of different objects. One of my favorite examples is an experiment by a team in Austria where they used fullerene molecules, those soccer ball shaped molecules that have 60 carbon atoms each in them. If they shoot that at a grating made of a silicon wafer with tiny slits cut in it, and look on the far side, they see a pattern of bright and dark stripes showing up in the number of fullerenes that arrive at various different positions. They see this pattern of bright and dark stripes, even for something as heavy as carbon-60 molecules, right, which are many thousands of times heavier than electrons. So this works even for great big molecules with lots and lots of atoms in them. But this double slit experiment with electrons raises a really interesting question, namely, what is the wave here? What is this wave really doing, right? And you can see that in this this experiment because the initial distribution of electrons looks very random, right? If you know where one electron arrives, you can't really say with any certainty where the next one is going to show up. But it's only through many, many repetitions of this experiment that you trace out this pattern and you see that there's really this wave nature. The fact that you can't predict any individual electron, but you can make a collective prediction about the results of many, many, many electrons, tells us that what we have here is a wave that's not a material wave in some medium, but it's a wave of probability. Knowing the wave nature of electrons tells us the probability of finding any given electron at a particular point. But we can't say with certainty that this electron will end up at this spot on the screen. All we can talk about is probability. This is a very deep issue at the heart of quantum physics, and this is something that lots of people find very disturbing about the theory. Among them, Albert Einstein, who, as we saw, played a crucial role in kicking the theory off. But this business of probability led him to one of his most famous quotes, which you can see here. Okay, it's in German because Einstein was German and he was writing to his friend Max Born, who was also German. I am not going to even attempt that. Here's the English translation. Einstein says to Born that quantum mechanics is imposing, but it's not yet the real thing. So the theory says a lot, but does not really bring us any closer to the secrets of the old one. I, at any rate, am convinced that he does not throw dice. Right. This is Einstein objecting to the probabilistic nature of quantum physics, to this idea that we can never say with certainty that this electron is going to end up at this particular place on the screen. We can only say that it has some probability of being in many different places. That's a profoundly disturbing idea to a classically trained physicist like Einstein. And this led him to ultimately reject the theory and abandon it in his later years, which is a real shame. But this is a really profound philosophical issue that bothered even people who were much more positively disposed toward quantum mechanics. Niels Bohr, who kicked the whole thing off with his quantum model of the atom, famously said that anyone who is not shocked by quantum theory has not understood it. Right? So there's profoundly weird stuff going on here that comes out of this notion that things that we think of as particles, like electrons, also have wave character to them at the same time. That everything in the universe is a particle and a wave at the same time. That's a really profoundly weird idea, okay? But one of the points of this module of this class is I hope that we've shown you that this is not an idea that physicists arrived at by accident, right? This is an idea that physicists were led to through a chain of evidence, right? Starting with things like trying to explain what is the color of a hot object. Why do hot objects glow that particular color red? right? In order to explain that, Max Planck had to resort to this quantum hypothesis, saying that light can be only emitted in integer multiples of some characteristic energy. Right. The photoelectric effect seems really simple, turns out to be really odd when you look at the results in detail. This could be explained, as Einstein showed, by assuming that light is a particle, a stream of particles, each carrying one unit of this characteristic energy. If you start looking at atoms, you find that, well, the structure of atoms is really strange. There should be this solar system sort of thing, but that can't work. Bohr proposed this quantum model that gives you the special orbits for electrons in which they don't emit radiation, and that explains the line spectra. But then you can't explain why those orbits are special unless you posit that electrons have wave character to them. And that leads you into this weird situation of an electron being a particle and a wave at the same time, of light being a wave and a particle at the same time. Those things are the core of the weirdness of quantum physics. Richard Feynman famously said that video I showed, the double slit experiment done with electrons, contains the central mystery of quantum physics. Everything else follows from that. So this is just a tiny taste of what's going on in quantum mechanics and what's weird and special about it. I'll put some supplemental reading up on Nexus if you want to look into those things a little bit more. Some extra chapters from books that I've written about quantum physics, about these particular stories and how they illustrate what's going on. Again, though, the biggest point that we'd like you to take away is that my printer over there is extremely noisy when it does this self-clean thing, and that's really rather irritating. Or, oh no, this is my kid printing homework. Fantastic, just what I need. The central lesson to take away from this, though, is about the process of science and how it works, right? Physicists don't invent ideas and then come up with theories to justify them. Physicists follow a chain of evidence. We look at the world around us. We think about models that might explain it. We test those models by doing further experiments and observations. And then once we've got a model that works, we share that widely with everybody else. So this is the core essential process of science. And this is the thing that I hope we've illustrated with all this talk about light being a wave and then a particle, electrons being particles, and then waves. So I hope this has been interesting. I hope this has been informative and showed you something useful about quantum physics, and also something about how science works. If you want to learn more about quantum physics, there's lots of other material. As I said, I'll put some chapters on Nexus for you to look at if you want. And that will be pretty much it for this class. Your final assignment for this module is going to be to write a short-ish, 3-ish pages paper in which you take one of the key observations that we've done in this class. The idea that light is a wave, as demonstrated by the Young interference experiments, the idea that light is a particle, as demonstrated by the photoelectric effect, or the idea that electrons have wave nature, as demonstrated by the quantum states of atoms. You should pick one of those 3 topics and write a brief explanatory essay, about 3 pages, explaining to a specific person who you should identify up front, someone who is another student at the same level as you, who's not in this class, or a relative who's not a scientist, younger sibling, or whoever you like, but clearly identify who the person is that you're writing to. Write an explanatory essay convincing them of one of those 3 things: that light is a wave because interference, light is a particle because photoelectric effect, or that electrons have wave character because of the quantum nature of atoms. That'll be your final assignment. The last thing that we want to have in this class, the last lecture that I'll do here, is I will do for each module, each group that comes through, I'll do one final lecture that's going to be kind of a Q&A thing. So if there are topics in quantum physics that you would like to know a little bit about, that you'd like to hear more about, there will be a form on Nexus for you to submit questions that you would like to hear answered, and we'll do kind of a mailbag podcast episode of this course, where I will take questions that you submit. I'll answer them in video form, and we'll put that up. So there'll be one unique video for each of the 5 groups that rotate through this modular course. So there'll be a kind of an Ask Me Anything option up on Nexus to submit that, and so please do that. And that will make up the last video that will appear in this 2-week module that we're doing. Otherwise, I hope you've learned something. I hope this has been enjoyable and as good an experience as we can make it under the very trying circumstances that we find ourselves in. And I wish you luck in the course and the rest of the course, and staying healthy, and hopefully all of us will be back together on campus in the fall. So thank you.